Three topics today. Two topics today because I'm going to skip second topic. Too tedious. You can take a look about the second topic. Second topic is a commercial. It's an algorithm used in commercial softwares. Okay, to find spline interpolation. Tedious. I skip this. Okay. Then in topic 3, I present a different type spline. Okay. Yeah. So far we use polynomials, right? Over each subinterval we use polynomials and then connect all the polynomials as a spline. Then different type. Okay. Section 4. Okay. Take a review. Take a review about some useful properties about basic splines. Yeah. Review. About basic splines. Okay. About the splines. Number 1. BIKX always greater than 0. Okay. Greater than or equal to 0. For any x, actually, for any, this symbol means any for any x. Second property is summation BIKX I from negative infinity to positive infinity is 1 for any x. Number 3. Okay, number 3. Alpha on this interval from T0 to Tn on this interval. Yeah. Only the following basis splines non-zero. Okay. Okay. Only the following B splines non-zero. Okay, say B negative K non-zero. BK negative K plus 1 non-zero, and then BK negative K plus 2 non-zero, and so then this is a Bn minus 1 K non-zero. Other B splines all on this interval everywhere is 0. Is 0. Property number 4, a basis. Okay, a basis. Property number 4. Okay. Consider these space S and K. The functions in S and K all defined on the interval A to B. Okay. Yeah. A to B. Now let me restrict the functions on log T0 to Tn. Consider. Then for this space, a basis is B negative K. Here, this guy. Okay. This guy defined on negative infinity to positive infinity, the domain. Okay. Okay, now let me restrict it on T0, TK, TN. Yeah. Yeah. And the last one, yeah, this one. Okay. B negative K plus 1, K, T0, TN. And then the last one here. K, T0, TN. Yeah. Yeah. This N plus K functions is a basis. Is a basis for this space. Okay, now this is a review. Now, spline interpolation. Yeah. Given a table of data about a function, yeah, given table. Y0, Y1, Y2, Yn. Okay. Y because I have used n here. Use n here. So how about let me change it? Say Q. Okay, Q. Y is equal to f of x. We don't know f. We just have a table of some values of f. We collect these values from experiments, the chemical experiments, physical experiments, something like that. Okay. Right. Now, spline interpolation. Okay. Find a spline function from this space such that, okay, the spline function at each log is equal to yi, okay, where I between 0 and q. This is a spline interpolation. Okay, now because I want to use this property. Yeah. This property restricts the function to this interval. So let me make assumption. Okay, here. Assume these nodes are in this space. Okay, make assumption in this space. Hey, now I can express a spline function in terms of the basis function. Yeah. Write spline function as a linear combination of the basis function. Alpha, say negative k times b negative k, then T0, Tn, yeah, then plus, okay, this is x plus alpha k negative k plus 1, then b negative k plus 1, k T0, Tn, x, then plus, plus, alpha n minus 1, b, n minus 1, k, T0, Tn, x. Because this is a basics, so any function can be written as a linear combination of the basis. If I assume x, yeah, x is in T0, Tn. If I assume, make this assumption, then this is equal to what? Is equal to just a B negative K, Kx. When X falls in this interval, retrieve function, the value is equal to the original function. Same here, yeah, here. Okay. This is equals to B negative K plus 1 K X. And this is B and K X. Okay, now let I assume X is from this interval. Then I can simplify this equation. Yeah, simplify the equation. Right? Okay. Simplify the equation. So as X is equal to alpha negative K, B negative K, K X plus alpha negative K plus 1, B negative K plus 1, K X, and plus, and last one, n minus 1, B, n minus 1, K X. Here I assume X is in T0, Tn. Okay, now I want S satisfies these conditions. Now I plug in the roots in X. Then I have S xi is equal to alpha negative K. Alpha will be determined. B negative K, K, xi plus alpha negative K plus 1. B negative K, K, xi plus alpha n minus 1, B n minus 1, K, xi. Yeah, this should be equal to yi. Okay, yi. What is I? I between 0 and Q. How many unknowns? Yeah. Unknowns. Alpha negative K, unknown. 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 How many unknowns? N plus K. So many unknowns. Yeah, from here. Yeah, from here. So many unknowns. How many equations? Q plus 1 equations. Yeah. How many equations? Q plus 1 equations. So solve this linear equation in matrix form. In matrix form, yeah. Let me solve it in matrix form. Let me write the linear system in matrix form. If I write the linear system in matrix form, then I have B negative K, 0, x0, the first row. B negative K plus 1, K, x0, B, n minus 1, K, x0, yeah. Coefficient matrix, first row, first equation, then unknown. Alpha negative K plus 1, alpha n minus 1, unknown. Unknown. Right hand side, the y values, right hand side. Yeah. Right hand side, y values. Y 0, y 1. How many equations? Q plus 1 equations. So YQ, yeah, the last y value is y cubed. So in total, 0 to q plus 1 equations. Second row is second equation. B x1 b negative k x1 b n minus 1 k x1. Second equation. I is 1. I is 2. Then we have third equation. Then the last equation. I is q. Okay. So the last equation is I is q. X cubed. Yeah. X cubed. Yeah. This looked. B level k plus 1 k x cubed b n minus 1 x cubed. Yeah, this is the linear system. So solve this linear system for alpha. Then we have a spline function that interpret this table. Right? This linear system is a well-conditioned linear system. That means that solve this linear system, the solution we can trust the solution because this linear system not sensitive to random error. Why? Look at the entries of this linear system. Okay, yeah. All right. First, row sum. Okay, each row. If you add them, okay, yeah, row sum is equal to 1 according to property. Yeah, is equal to 1. Yeah, this is a 1. 1. And also each entry non-negative. Yeah, basic spline functions non-negative, always greater than or equal to 0. So yeah, each entry greater than 0. And the summation always 1. That means that each entry always between 0 and 1. So in this matrix, low entry is too large. You agree? Low entry is too large. It doesn't like power, okay? Power, yeah. If a load is, say, 100 large, power is 100, then 100 to 100, this is a very huge number. It doesn't like, the power basis. Yeah. So, yeah, each entry between 0 and 1, and their sum is always 1. So, as a result, low entry in this matrix is too large and or too small, actually. Because their sum is 1. So your computer, cannot ignore any of these entries. So as a result, this matrix very stable computational. So yeah, actually, this is what a commercial software to solve a spline interpolation problem. For the algorithm, you can find in the second topic. Okay, the second topic is on my note. Too very, very tedious, so I skip the second topic. So, yeah. Hey, this is topic 1. Topic 2 today, tensor spline. Okay, a different type of spline. Yeah, we don't use polynomial over each interval. Second topic. What time? Tension. Right. This is from section 6.4. In the first book, okay, in the first book, we have 3 books. Tension, spline, tension splines, tension splines. Here, we also consider interval AB. Consider interval AB. Yeah. Functions are defined on this interval. Interval AB. Yeah. A, B. Also, we cut interval into sub-intervals. Cut T0, T1, T2, T3, Tn, Tn minus 1, Tn, okay. Okay, now from A to T1, it is a function, not necessary to be polynomial in this tension spline. Yeah. From T1 to T2, some function, okay, yeah, may not be polynomial. T2 to T3, some function, and so on. Here is Tn minus 1 to B, okay, yeah, skip Tn, some function. Now, tension spline, we want to find a function that has the following properties. Yeah. The tension spline. Tension spline, it is a function. Let me give a name to this function. Yeah, according to the book, use capital T X. Capital T means tension spline. The tension spline is defined on AB, the interval AB, and satisfies the following properties. Number one. Okay. I need to given a table. Okay. Let me give a table. Okay. Here. Okay. Let me give a table. X. In log zero. In log zero, I require the tension T, the value is beta 0. T1, beta 1. T2, beta 2. How many T points? Tn, beta n. Okay. Let me give values at the lot. Okay, yeah. Suppose that this value below. Okay, suppose below this value. Right. Okay. Now attention spline defined from on this interval and satisfy. Okay, yeah. This function. T at Ti, right? Ti. Tk is equal to beta k. What is k? K is 0, 1, 2, n. So actually, the beta values we can arbitrarily given, given, and find a function through these beta values. Right. Second, we require smoothness about function t. We require t is in C2 AB. That means that t has derivative of order 2. Take derivative once, take derivative twice, and all the derivatives continuous. Yeah. A smoothness we require. Number three. On how about, let me write here. Okay. Number three, property number three. Property number three. On each of the following interval, A to T1, yeah, the first interval, A to T1, skip T0. T1 to T2, T2 to T3, and so on. And then Tn-1 to B. Yeah, skip Tn. On each of the interval, we require the spline function. Yeah, T of x satisfies this differential equation. Yeah. T derivative 4, take derivative 4 times, minus a tau some parameter, some parameter, tau squared times t, second derivative is 0. Yeah, here we only requires second derivative continuous from A to B. Now, take derivative 4 times exists, but may not be continuous from A to B. Yeah. Just over each subinterval. This T satisfies this differential equation. Differential equation. Yeah. This is if you can find such a T, then this T is called tensor spline. Okay. All right. Now let me explain this parameter. This parameter. Remark. Okay. When tau is 0, yeah. When tau is 0, differential equation becomes, let me give a name, 1. Differential equation becomes 1, becomes tau, a t, take derivative 4 times is equal to 0. How to find t? Easy to find t. Yeah. Some function take derivative 4 times, it is 0. then this implies that derivative 3 times is a number. Do you agree? Do you agree? A number, say a number, I have used A. Say number C1, okay, number C1. Derivative 3 times is a number. Derivative twice is what? Twice is C1 x plus C2. Do you agree? Then this is 1/2 C1 x2 C2 x plus C3, right? So actually, T satisfies this differential equation. T is a polynomial of degree 3. So yeah, undo this derivative, then we get T is what? 1/6 C1 x3 plus 1/2 C2 x2 C3 x plus C4, right? C4. If you set this parameter 0, then over each subinterval, spline function is a polynomial of degree 3. And also satisfy this condition. So when tau is 0, T tensor spline is the spline that we learned is a spline in the previous section of degree 3. Actually, cubic spline. Yeah, over each subinterval, polynomial of degree 3. Then there is a cubic spline. Yeah, that we learned. This is a 0. How about the other extreme case? Tau is infinity. Yeah. Okay. See. Okay. Tau is infinity. Yeah. When tau is infinity, then what is tensor spline? Okay. When tau is infinity, okay, then from 1, I divide tau square. Okay. T. Yeah. Divide equation 1 by tau square, then I get this equation. Now tau is infinity, so first term is 0. So this is a tau, T. Second derivative is 0. Second derivative is 0. T is a linear function. So this is a linear function. Yeah. C1 x plus C2 linear. So when tau is infinity, tensor spline is spline of degree 1 over each subinterval. T tensor spline is a linear function. So linear function. Yeah. This is a spline of degree 1. How about between 0 and infinity? Then T is not a polynomial. Okay. Yeah. So okay. Okay. How about between 0 and infinity? We need to okay. Okay. How is between 0 and infinity? Then we need to solve initial and boundary value problem. Yeah, we need to solve. Okay, yeah, over each subinterval t satisfy this equation. Okay, yeah, so t4 minus t tau squared t second derivative 0. We need to solve this linear system. Okay, this is t x is between say tk plus 1 over each subinterval satisfy this equation. Say over this subinterval, yeah, t satisfy this equation, and at the boundary of this interval, boundary, yeah, this and this, t at tk is beta k. What is beta k? We are given at the beginning. Yeah. Okay, and then tk plus 1 at the other endpoint, beta k plus 1. Beta, suppose below. Suppose below. Yeah, this guy below. Yeah, below, suppose below. Derivative order 4. When we recover t, we will see there are 4 integration constants. 4 integration constants, 2 conditions not sufficient to determine 4 integration constants. Okay. Now, second derivative, yeah, is ck. What is ck? ck plus 1. Here is unknown. Will be determined. So between 0 and infinity, we need to solve this. This is a boundary value problem, not initial value problem. Initial value problem is the time is 0 initial. This is a boundary. Yeah, the solution of this problem, we can write it down, but no longer to be polynomial. Solution is the solution. Let me give a name to this problem. Say problem number 2. The solution to problem number 2 is T is ck. Yeah, what is ck at this point? Unknown. Sin this function, yeah, h, yeah. This function, yeah. Sin x is ex minus e lambda x over 2. So this is how tk plus 1 tk below, it is a lot below. Okay. Minus x, what is x? Yeah, this x. And then plus ck plus 1 below. Ck plus 1, we don't know. Okay. We don't know. we don't know. Will be determined. And then C H R X minus TK. And then over tau squared C tau HK. What is HK? HK means TK plus 1 minus TK. So HK below. Yeah, this guy below. Tau below. Okay. Yeah. You can give a value to tau beforehand. Okay, between 0 and infinity. Say, I assign say level 3 to tau. So. Yeah. And then pass beta k, beta k below. Okay. The table at the beginning. Yeah. Beta k. Beta k, we arbitrarily assign values to beta. Then minus ck, we don't know, over tau squared. Tk plus 1 minus x. Then over hk. Then plus tk k plus 1 over tau squared. X minus tk. So when tau is 0, this function is polynomial of degree 3. Polynomial of degree. When tau is infinity, this function is polynomial of degree 1. Between 0 and infinity, no longer to be a polynomial. Look like this. Tensor spline has many applications, just like cubic spline. Yeah. Tau, we can adjust tau. Okay, we can adjust tau. Okay, when tau is large, this function tend to linear the curve, close to a line. When tau is small, this curve close to a cubic polynomial. We can adjust. So people call tau, view tau as a force. A force. Yeah. Tau is large, then stretch the curve so that the curve tend to be a straight line. When tau is small, release the curve. The curve look like the graph of a cubic polynomial. So yeah, this is people view this as a force. That's why. Or a tension. Tension means is parameter. That's why people call this spline function. Tension spline. Tension spline. It has applications in engineering. So I don't go into detail. Impossible because too tedious. Too tedious. You can take a look at my notes. Now I have finished today chapter 6. Friday we studied chapter 7. Chapter 7. Chapter 7. Chapter 7 is about integral. How to numerically compute an integral. How to numerically compute derivative. Remember, in this course, a function, we don't have a formula for this function. We just have a table of function values at some points. Now, we only have a table of the function at some points. How to compute derivative accurately? How to compute derivative at some point? Say at some point. How to compute based on a finite, based on limited information about this function. How to accurately compute derivative at a point. This is what we will learn in chapter 7. Yeah. How to compute derivative and how to compute integral. We don't have formula for f. We just have a table of data. Then how to accurately compute an integral. This is what we will do in chapter 6. Now I'm done with chapter 6 today. Okay.